this lecture, we're going to talk about the pressure inside a soap bubble. Let's see what happens to a bubble when it gets bigger and bigger and bigger. Now, I'm putting more and more air into it. You might say, well, what does that mean? More pressure or less pressure? Is it like a bicycle tire, where when you want to have more air into it, you have to increase the pressure? So as this gets bigger and bigger and bigger, the radius gets bigger and bigger and bigger. And I guess intuitively you can say the curve is getting less and less and less. Think about a trampoline. One or two people on it, fairly flat. The whole class gets on it, boy, it's curved. Well, let's have a look at pressure as it relates to the size of a soap bubble. So what I'm going to do is put two bubbles together. I'm going to make a large one here. Like that. And let's make a smaller one here. Whoops. There we go. Well, they're almost the same. So I think I'm just going to open up this tap, and because the pressure can't be exactly the same. So we'll see what happens. As I open the tap, air will move from one to the other, I hope, and it will go from an area of high pressure to an area of low pressure. Now, is anything happening? The small bubble is pushing air into the big bubble. That means the pressure is the greatest inside the small bubble. So we can infer that as I was making that bubble bigger and bigger and bigger, the pressure inside was getting less and less and less. Let's look at that with a little bit of math. So surface tension, and that's the stretchiness of the soap film, is the force per unit length. In other words, if you have a length of soap film, it'll pull with a force is proportional to something called the surface tension. The pressure inside a soap film is pressure's force per unit area. Now if we look at a soap film or a bubble like that, I'm just going to cut it in half, and the top part is being pulled down on this area here. Now remember, now look at if we take this, surface tension is force per unit length, so that means that the force acting is equal to the surface tension times the length. Well, what length do we have here? Well, we have all of this soap film here. All of this edge, all the way around here. Imagine we cut this sphere in half. We have all of that length. If the soap bubble has a radius r, then this length would be pi 2r, right? Pi 2r is the distance around a circle. So what is the force? Well, the force is equal to the surface tension times the length. Surface tension times pi 2r. Now that's acting on an area here. Well, what is this area here, this hatched area here? It's pi r squared. Area is pi r squared. And so the pressure which is force per unit area, the pressure is going to equal force, surface tension, pi 2r, divided by area, pi r squared. Now a lot of things, the r's, this r cancels, so we left with one r here, pi and surface tension and 2, they're all constants. So we can say that pressure is proportional to some constant times 1 over r. Now think about it, what does that mean? That means when r gets bigger, the pressure gets less. And when the pressure gets more, r gets larger. So as the pressure increases, the radius gets less. I'm going to look at this in a slightly different way, because this tends to make you think that a curved surface means pressure. That doesn't mean pressure all the time. So we have a bubble here, and it's between two rings. And if I pull this down a bit, you'll see we have a bubble that looks like a cylinder here, but the ends are spheres. If I break the ends and break the middle, I have a very interesting shape. It is a curve that has a radius r to the outside and a curve that has a radius r to the inside, and those r's cancel each other out. I don't know, it might be, I'm trying to just diagram that, but we have a curve to the outside with a radius r, and we have a curve to the inside with a radius r. And those r's are the same. So that means that the pressure being exerted by this curve is exactly opposed by the pressure exerted by this curve. And so this actually acts like a flat surface. This is called a catenary. So there's a lot of neat things about pressure and soap bubbles, and I hope you'll be interested in studying more.